So where do we go from here? Okay. So if I could characterize the last 10 years, I would say it's been characterized by bigger is better. We use the big hammer, and that's great. That's gotten us a huge increase in production, and that's what was needed. Okay. That was driven by an enormous amount of pent-up demand that was in the U.S. If you think about it, the U.S. domestic supply had declined for a period of more than 20 or 30 years from its peak, and it's not easy to fill a supply gap that's that big. And as an industry, our industry did it with this giant hammer. So obviously the economic conditions are such that we can't continue to keep, it doesn't make sense to do that anymore, right? So we're sort of at a crossroads now. What are we going to do differently? Well, we're in a position now, of course, the economics are different, the landscape is different. We have the tools, we've developed the tools. Let's, instead of using the big hammer all the time, let's do fit for purpose. Let's use the right tool for the job that we're trying to solve. And I'm going to talk a little bit about that. And I'm going to say that what we're going to do in the next 10 years is going to be driven by the need for an abundant, low-cost, low-impact energy source, right? So rather than trying to fill a supply gap, which doesn't really seem to exist anymore, but there will always be a demand for oil and gas. We're going to need that resource in the future, but let's look at it as a fit-for-purpose type environment. So what do I mean by fit-for-purpose completions? I'm going to think of it a little bit as I want to coax the best that I can out of the reservoir. I want to bring the best out of that reservoir. There are several considerations that are important here, and I'm not going to touch on everything that's important, but I'm going to talk about what I think, at least in low permeability reservoirs, are some of the critical takeaways, some of the critical considerations as a reservoir engineer or completion engineer you have to think of when you're designing a completion. So obviously total frac surface area, probably the most important thing, right? How much frac surface area do I need? How does that relate to treatment size? Another one is frac complexity, right? You hear a lot of people in the industry talking about frac complexity. In fact, I think frac complexity is somewhat of a controversial topic. There's people out there that are in the camp of, I can create fracture complexity with the frac treatment I'm doing. There's folks out there that say you can't influence that at all, and it's entirely Mother Nature. There's people out there that say there is no such thing as frac complexity. So we're going to talk a little bit about that. Maybe I'll say some things that are controversial. Hopefully it'll be interesting anyways. Frac conductivity. This is another one where there's a lot of controversy, right? There's a lot of discussion back and forth. Is how important is frac conductivity? I'm going to give you my thoughts on that. Okay, but these are important considerations because these are high dollar things you're spending your money on. Completion compartmentalization, easy for me to say, which really relates to frac stage density. Okay, so how many stages do I need? That's obviously another huge consideration. Well placement, this is one that's critically important in certain cases, and we'll talk a little bit about that. Where do I land that well, right? And what sort of trajectory do I use? And then completion technology. This deserves a lot more detail than I'm going to give it today, but I'm just going to give you a couple of simple examples. But completion technology is important, and a lot of times as an industry we don't necessarily, we look at cost as being the main driving factor, but it's much more than that, right? You have to look at not only the cost, but how the benefit on the other end of it, how it's going to affect production, and look at it more as a net present value type thing. So the name of the game here is maximize effectiveness and reliability, minimize waste. You can think of well performance as a chain, okay? You don't get performance out of a well unless all of these elements come together. There's always going to be a weak link in that chain somewhere, and usually that weak link, or I'm going to say always that weak link, is what's going to drive performance. Whatever that weak link is, that's the thing that if you change it a little bit, it's going to either kill your well or make it way better. If you put a lot of effort into a link that's already strong, you can do it and you'll still get a good well, but you're kind of wasteful by doing that. Okay? This is the best analogy I can think of, and I'll give you a couple different examples. One is designing high connectivity fracs in liquids-rich plays. And I already know by saying that that's a very controversial statement. And I'm going to I'm going to talk more about that, so you'll see why I have that opinion that that's the case. This one I think most people would agree with, using high frac stage density in what we would call, micromillidarcy, higher permeability. What you're really doing there is you're bolstering one of those links that's already strong. So it's not necessarily a bad thing. It's not going to negatively impact the well, but it's going to negatively impact your economics potentially. Okay, so the trick is really identifying what is that production driver and designing your completion around that. That's really what I mean by fit for purpose completion. So I want to show you some examples. Let's talk about frac surface area first of all. And you'll never know it's not permeability. We joked about this because from a reservoir engineering perspective, really our job is to look at what comes out of the wellhead. So how do I really know there's a frac down there? These equations tell me I don't necessarily know, because once I have a stabilized production rate, I can make this look exactly like this, or vice versa. I can make this look exactly like this. These are obviously very different well geometries, different permeabilities, but in terms of their stabilized production rate, I can make them exactly equal. And you would never know which one was which. And so we've always had this issue, right? When we, as reservoir engineers, we analyze production data, we don't know how much of it is because of frac area and how much is because of permeability. We have to use other metrics to understand that. But we can use these equations in our favor, basically as a way of calculating how much frac area we need. And this is sort of basic tool in the toolkit of the reservoir engineer. But a lot of times I find that these very simple calculations are not used in completion design. And they really should be. They should be used more. You can calculate how much frac area you need to achieve the production rates that you want to achieve. Okay? We can do that. And it's not always going to be the same frac area, surprise, surprise. If you have a higher permeability reservoir, you don't need as much frac area. So one way to think about this, in this specific example, I've got, let's say I've got a 1 millidarcy conventional reservoir, and I want to be able to reproduce the same stabilized production rate out of a reservoir that's got 1,000 times lower permeability. How am I going to do that? Well, this equation tells me how I can do that. In order to, for every foot into the reservoir I want to drain, I'm going to need 100 feet of frac length, or frac half length, to obtain that same production from that 1 millidarcy well. And you can use that at scalable to any permeability you want, right? So that equation works great. We use that one all the time. It's nice, we've got software and more advanced modeling. We can run the models that do this in a lot more detail and take into account the time and the transients and all that sort of stuff. But you should always do this because this is a gut check, right? And the software can just support that for the most part. So if we want to drain a quarter section in this example, we would actually need 13,000 and change feet of frac length. And that's, that would be impossible to achieve. So I guess what I'm saying is that if you have that reservoir rock that's 0.001 millidarcies, and we're exploiting rock that's a lot lower permeability than that. But if you want to be able to produce commercial production rates out of that, you're going to need 13,000 feet of frac length. And we can't accomplish that with one single vertical fracture. So this is where completion compartmentalization comes into play. Okay? I want to be able to deliver that 13,000 feet in staged completions, or staged delivery of that stimulation. And that allows me to efficiently create that 13,000 feet and get a great well out of it, get some sort of reasonable recovery rate of that resource. To illustrate the point, and this is real data, this is a log-log plot of production. And one is a vertical. You don't see too many vertical single-stage fractured wells anymore, but they are still kicking around. Most of them have been on production for many, many, many years. So there's a lot. There are a few of these around. This particular one has been on production for 200 months. And this straight line with a b-value of 2 tells you that it hasn't seen any boundaries. So stimulated well, on the other hand, saw the boundaries after 18 days of production. And has multiples of better production rate out of basically the same rock. So compartmentalized completions have allowed us to do a couple things. One is create economic wells out of really crappy rock, and the other one is dramatically accelerate resource recovery in tight reservoirs, much more than we'd be able to do with just simple single-stage fracturing. Now we're at the point where we can actually optimize this. Okay, so that's the sort of the simple concept. Taking this to its extreme, we can look at cases and run these scenarios. Now we're getting beyond just back of the napkin calculations. We have to run these through reservoir simulators and economics. But basically, what you end up with is a discounted cash flow forecast. This is net present value shown on the right-hand side. And what I'm doing here is comparing the economics of running various different stage spacings from 15 meters all the way to 150 meters. That's your break even right there. Obviously, if you're going to do 15 meters, you've got a very, very high treatment intensity. And you're going to start with a lot of sunk D&C cost here. And obviously, the economics in that case don't support it. It shows it very clearly there. So if we really wanted the optimized completion in this case, we could choose, really the yellow and the green are overlaying each other, so we could choose anywhere from, say, 60 to 75 meters. And you probably choose 75 meters because you spend a little bit less money on the front end. And that gives you your best net present value. Okay? So we need to have all the information to plug in there. It's equal parts Darcy's law and depletion and reservoir engineering along with economics. And we put those two things together and we can solve that problem quite nicely. All right, what about frac conductivity? This is where things are going to probably get a little controversial and happy to engage in conversation on this because I know even within our team we've had lots of arguments about this. But if I could distill it down to just a couple of very, very key points that I think are important. And if nothing else, we won't get into the details of the equations and everything. But what I want to make a couple of points. One of them is that yes, of course, you always have to have frac conductivity. Okay? If your frac doesn't have conductivity, it's not going to flow. What's important really is that frac conductivity, you can think of it a little bit as being graded on the curve. Okay? I remember when I went to university, a lot of our courses were graded on the curve. So if the performance in the class was on average very poor, you didn't really need to have to get a good mark, that good of a mark on the test to get an A. All you had to do was be the best in your class. The best in your class might have been 50% or 60%, right? I actually had a class like that, where I think 60% was like one of two actual passing grades, and that person got an A. It wasn't me. I failed. I was lower down in the pack. I failed the test, but I still passed the course. That's how hard it was. So I think of that. To me, that was a good analogy of what frac conductivity is like. Okay. And so let's think about reservoirs. There's two things in reservoirs that are important when we talk about conductivity. One of them is the viscosity of the fluid, and the other one is the permeability or flow capacity of the rock. And we put those two things together, one over top of the other, K over mu, and we call that mobility. Okay? So it depends on the rock itself, and it also depends on the fluid, not the fluid you produce at the wellhead, but the fluid that's flowing in the pore space. Those are the only two things that matter. And so if you have, I'm going to take two extremes. If you have a very low permeability rock and something like oil sitting inside it, which has very low mobility, oil has 50 to 100 times lower mobility than gas. So when you take those two things and combine them together, that becomes the weak link in your chain. The matrix fluid mobility is very poor. So the matrix and the fluid is struggling to deliver anything to that frac. That's the analogy of that is like my class that I took. I don't need to get that good of a mark to pass that course, right? My high strength proppants or designing for a huge amount of conductivity in that frac, you're overcapitalizing. You just don't need it. You need some conductivity, but you don't need that much. And I'm purposely talking in qualitatives here. I'm not giving numbers because I don't want to get into that, but certainly from a qualitative sense, this is true. On the other hand, if you're talking about a higher perm reservoir with gas, the opposite is going to be true. Now your frac actually becomes the weak link. Your frac becomes a choke point. So you can actually have a situation, and compounded with gas because you can get things like non-Darcy flow. Not talking about you, Darcy. I'm talking about different Darcy, but that's a terrible joke. Sorry. Non-Darcy flow can cause this choke point as well. So the ability of the formation and the fluid to deliver flow into the frac is really going to dominate what sort of conductivity you need. So those are my comments on conductivity. Now let's talk about frac complexity. A couple of points I want to make here. Frac complexity, I think, is Again, this is going to come down to oil and gas. I think frac complexity is going to be critical for ultra-tight oil, and this is why. If we take two examples, oil and gas, the top crude diagram here is supposed to show complexity. The bottom is supposed to show when you don't have any complexity. Here's my perspective. I have no idea whether the reservoir has frac complexity or not. All I can do as my area of expertise is analyzing the production data, and I'm making inferences based on my analysis of that production data. And what I can tell you is that when I look at production data, it always appears that the oil reservoirs have, from the RTA that we do, they have this evidence of enhanced permeability and this evidence of we've made an inference that it's frac complexity. And we argued about it we argued about it actually quite a bit yesterday and in the days leading up to this talk. What does that really mean? Does that mean we're creating frac complexity in oil reservoirs? I think the answer is no. I think the frac complexity is either there or it's not. It's Mother Nature that puts it there. But what I will say is that if you saturate the pore space with oil in an ultra-tight rock, you're not going to get any sort of Darcy flow through the porous media. You're only going to get flow through the fractures. So in order to get any sort of commercial oil, economic oil rates, you have to have some sort of fracture complexity in that oil well. The same is not necessarily true for gas. Gas molecules are much smaller. Gas is much more mobile. Still, in a non-complex situation, you can still get gas production. So in a gas scenario, you can get a great well if you have fracture complexity. So fracture complexity is always going to be beneficial, but it's going to really be a distinguishing factor between a good well and a poor well if oil is the fluid. So frac complexity creates a multiplicity of total frac area. That's a great thing to have. Obviously, it's going to add a huge amount of productive capability to any reservoir. But frac complexity is a dominant performance driver in ultra-tight oil-saturated reservoirs. I think that's a really important statement that maybe the industry doesn't quite, particularly from the completion side, doesn't quite grasp and understand. Certainly, we don't necessarily apply this to the way we design all of our oil completions. Frac complexity, it's not that it's not important for gas, it is, but it's less important. It's less of a driving mechanism. We can still get good gas wells with purely just planar fracs and no complexity. And the reason I'm saying these things is because I've analyzed hundreds of these wells using rate transient analysis, and this is what we see from the production analysis. Influence of treatment design on frac complexity, I believe, is minimal. Can we influence and create complexity? Maybe a little bit, but Mother Nature accounts for that much of it. If the rock is not naturally going to break in a complex manner, there's little that you can do from a stimulation perspective to make that any better. So how do we create complexity where it doesn't exist? Well, we do it artificially by compartmentalizing our completion, right? We put more stages in there. So if we can't have natural complexity, we need to double up on our stage spacing and artificially create that complexity by compartmentalizing and creating more fractures. Next thing I want to talk about is well placement. You guys have seen some of this already in previous talks, one that Adam presented, and I think John presented one as well. This is something that we believe is very important. This is not rocket science. It's very simple, but I think it's an undervalued variable when many operating companies are thinking about well placement. Okay, where do you land your well? A lot of operators will answer that question, well, I'm going to land my well in the place that has the best porosity. My target depth, if I look at a log, my target depth is going to be in that place where I think I have the best hydrocarbon pore volume, the best hydrocarbon porosity. And that's, of course, that makes sense, right? That shouldn't be a mistake. I mean, that should make a lot of sense. But if you look at this example, in a lot of cases, and this is just a frac model run in a low perm reservoir with significant gross pay thickness, the landing depth on here is in the best porosity. But you can see a lot of the fracture progresses downward, and only about 100 feet of that fracture is effective. The rest of it is ineffective at the bottom because the viscous forces can't overcome the gravity forces and you can't lift those liquids out of the bottom of that frac. Very, very simple, simple physics there. Make gravity your friend. So in the other frac model, we put the perf site 50 feet lower towards the bottom. You're going to be careful, if there is water down here, you don't want to put it too low. So designing where that landing target should be is not simple. Okay, we don't want to oversimplify it, but it's not necessarily going to be in the spot where the best porosity is. If you land it lower, then we can actually make much more of that frac height effective because you're making gravity work for you, not against you. Let's talk about one more thing, and that's the impact of completion technology. This is the subtlety that a lot of people don't see, but it's, the Anderson-Thompson team works with NCS obviously on a regular basis, and this is a big part of our research in the past is looking at, for example, how what sort of reservoir value can be provided by pinpoint completions. And I'm going to make this a little bit simpler and just say, let's look at the impact of cluster effectiveness. 98 or something % of all the wells, that might not be the right statistic, but it's above 90% of all the wells that are drilled, tight gas, tight oil wells drilled in the lower 48 in the United States are cemented liner plug and perf wells. So perf cluster effectiveness is a huge deal, right? It's going to be, even if it's only like a 1 or 2% difference, it's going to be in 98 or whatever is 95% of the wells. It's going to be something that we have to consider. So if we only have, and the pervasive thought in the industry, and most people would agree, there's lots of literature to support this, is that we're really only getting about 50% effectiveness in a plug and perf type completion with the technology that we have right now. If we simulate that, we get a picture that looks something like this. And it's not a bad thing. It just shows you basically that the red spots, all the sort of heat map, the red spots in here are areas that aren't being drained efficiently. Okay? And the green spots and the blue spots are areas that we're draining more efficiently. That's what 50% cluster effectiveness looks like. So multiply that by basically almost every single well that's drilled in the lower 48. Okay? This is the sort of picture that we're getting. In Canada, the landscape is a little bit different. There's a lot more open hole completions. And we're not, I don't really know how to simulate production response from open hole completions because we're not necessarily sure where the fracs are going. So it's a lot easier to compare 50% effectiveness in a cemented completion with 100% effectiveness in a cemented completion. And that's what it looks like when we run those models. This concept, this idea, we're putting into a paper that we're going to be presenting at CURC in February. So there'll be a lot more coming on this. But if we take this now and translate it into actual recovery profiles for the 50% and 100% case, there is a measurable difference. And in this particular example, I forget what the permeability was, but it was a tight reservoir. I think we took reservoir characteristics that would be indicative of something. What we see in the first 5 years is we already have an uplift of about 150,000 barrels from just going from 50 to 100%. And that equates to about $7.5 million at $50 oil. So it's significant. So let's review, and I'll go through these ones pretty quick. But the idea here is let's look at the full landscape of all these plays, and we're looking at a permeability scale here. And really, again, all I want to do here is, and I don't put any numbers on here, I'm not trying to get into the details, I just want to show in a relative sense what's important in low permeability completions and what's important in higher permeability completions. This is all what I would call conventional tight being the high perm scale and ultra tight being the low perm scale. So what's important in ultra tight, very low permeability, is frac area and stage spacing. What's important in conventional tight is frac conductivity and well spacing. I didn't really get into well spacing, but that's going to be a critical driver in higher perm plays because we start to reach the boundaries of volumetric boundaries of well spacing a lot quicker. So it becomes a much more important consideration. The other thing I want to look at is liquid content, because whether you're doing a completion for gas or whether you're doing a completion for oil is going to be a critical difference in how you want to design that. So for dry gas, Frac area, frac conductivity are going to be more important. For black oil, well placement, that's what I talked about, making gravity your friend. That's going to be critically important. Fracture complexity, we already talked about that. That's going to be critically important for oil cases. One of the reasons I wanted to do these two plots and show specific examples of plays that are there is to really indicate that the areas that we're the most interested in oftentimes are in this middle area, which makes it more difficult, right? If we were on one end of the end members, then we know, there's going to be this one dominant thing that's really important. But a lot of times we're kind of in this gray area where we have to consider all of these things together. How much performance is coming from the reservoir rock itself? How much is really dominated by the fractures? Sometimes we're kind of in this middle zone, this no man's land, which makes it challenging, right? As an industry, building that fit for purpose completion can be very challenging.